I am Dr. Rashid Ahmed from the Department of Physics of Kohart University of Science and Technology. In the subject of Quantum Mechanics 1 with the course code PHY 212, we are at the lecture number 21 and the topic is the superposition principle. In quantum mechanics, we know that when we make a measurement on some system of some observable, then we get some value for that observable. But if we repeat this measurement on a similar system with exactly the same specifications, we might not get the same value for that observable. And even if we make a large replicas of the same system and do the measurements one by one on all the members and all the replicas, we will not get the same value every time. So rather than expecting some exact value, then we say that we have to calculate the average or expectation value. This phenomena of having a large replica and values coming out are not same is due to the superposition principle. So in today's lecture, we will try to understand what is the superposition principle and how different states in which a particle could exist superimpose on each other and at the end give us some average value. So let's start with the well-known example of a particle in a box. And in this particle in a box, we will first talk about the state of the system. And we will see that how we can describe a particle in a box with some particular state. So imagine that this psi is the state function which is at the initial time, that is t is equal to 0. And this is at the x-axis we have the position of the particle. And imagine that the initially at the time is equal to 0, the state of the system is like this. So it is just randomly chosen distribution just to illustrate the superposition principle. Imagine that this is a particle in a box which has some position and the width of the box is from 0 to a, and this is the state of the system. So first thing to establish the superposition principle is to make the large number of replicas of the same system with the same wave function at initial time. So let's do that. So we call it an ensemble average. So we want to create a large number of identical replicas, which we will call it as an ensemble. So this is an ensemble at time t is equal to 0. So at initially, we can set some other value as well, but let for convenience take t is equal to 0. And then this is the pictorial representation of this ensemble. So you can see in the first case, the first member is in the state psi x0. This is the initial state of all the members of the ensemble. And then we have the second member, exactly the same copy of the first member. And then we have the third member, which is the exactly same copy of the other two. And so on, if we go up to the nth member, so you can see that it is also the exact copy of. So all of them are exactly same in all respects. All the parameters for them are exactly the same. So that means if we calculate something, for example, energy, momentum, or any other observable, the value which comes out from the first member shall be equal to the value which comes out from the second member, because all other things are same. So why not that values coming from all the members of the ensemble when we make measurements on them are exactly the same. But we know that the law of nature or the law of quantum mechanics says that the value which we calculate for any observable from these members comes out different from the second member and third member and so on. So at the end, then this question that what would be the value of some observable becomes irrelevant. And then we don't ask this question, because this question is not correct to ask what is the value of some observable. But the correct question is that what is the probability of having that value? That's an important point. That's why I repeat that the question that what is the value of an observable for some member of the ensemble. It's not a correct question to answer, to ask. The correct question is that what is the probability of having some particular value? And for that reason, we have to calculate the average and probabilities. And for that reason, we say that the quantum mechanics is inherently is a superposition of different states. So this first state, second state, and third state all are does exist in superposition, and we get the average values. Okay, so as I said that if this here we have constructed the ensemble of all members. Let's say if time is passing, here we have t is equal to 0, but time is passing, and at the later time, if you want to see that what will be the ensemble of it, so you can see that first member and second member and third member and nth member all are exactly the same after passing some time. But we have not made measurements yet. What if we make a measurement of some observable, and what value we will get? So let's take the measurement at t is equal to t plus epsilon, and let's consider the observable to be the energy. This is just an illustrative example of what we have already said, that we take the observable energy and we measure the energy in every ensemble of the every member of the ensemble, that is in identical replicas, at time t is equal to t plus epsilon, where epsilon is a small increment in the time. If we do this measurement, so what we get out? For example, E1. So this is the state of the system at time t plus epsilon. Here you can see, and it is in phi 1. So what we see, that it could be E1, it could be E5, that is it is in the state 5. Excuse me, and it could be E3, it could be E1 again. So the question is not that which value of energy we will get, but the right question is what is the probability. So quantum mechanics is not telling us exact values, but it is telling us, its laws actually can tell us only about the probabilities of having, let's say, E1. Let's say we can ask what is the probability of finding out E1 in the ensemble 1, in the first member of the ensemble, or what is the probability of finding out E1 in the second member, and so on. So let's make this statement concrete with some mathematical calculations, and later on with some examples. So as I already said that the question, that is what will be the energy of each box, is not correct. So energy for each sample, because each sample is different. So better question is that what is the average of the energies measured in all boxes of the ensemble, and later on we can just calculate the probability of our finding any value, rather than, so first we calculate the average, our expectation value, and then later we calculate the probability for any value to be found out. So let's define it mathematically. Probability of finding the energy. So the probability of the finding the energy, or the expectation value. So this is the expectation of energy, which is an observable for Hamiltonian. We can have different observable. For example, we can have position, or we can have momentum, and so on. Those observables which we quantize. By the way, we cannot have mass, because we do not quantize mass or time. So we cannot have mass or time, but the quantizable observables are energy, momentum, and angular momentum. So here we have taken the example of energy. Okay, and this is the expectation value defined in terms of probabilities. So this is the probability of finding the En. En could be E1, E2, E3, or whatever. These are the energies in different states, and this is the En multiplied. So this formula we have already derived when we were talking about the expectation values, but this is the expectation value for energy. So the expectation value can also be written as like in bracket notation. You can also put it in this form, where H is the Hamiltonian, which corresponds to the observable E. So we can also make calculations from here exactly, or we can do it in terms of probabilities. Okay, so the expectation value, then once we have the expectation value, which can be written in this form, then it is good to find out the eigenstates which obey this equation. For example, when h hat, which is an operator corresponding to energy, when it acts on psi, so what could be the psi is? What are the possibilities for psi which obey this equation? Okay. So here we know that we can write this psi in form of this equation in form of Schrodinger equation. That is, when h acts on phi n, it gives us the energy E n and phi n. So the correct form of this psi would be when we expand this psi in terms of this phi, which is the solution of the Schrodinger equation. So when we can, for example, what we do, that we can form the Hilbert space which comprised of these state functions or this basis, and then we can expand this psi in terms of these bases which are the eigen states of the Hamiltonian. So this is a consistent picture that to calculate the expectation value of E, this psi must be expanded in the basis of some Hilbert space. Okay. So expansion of this space, these eigenstates in terms of the Hilbert space where Hamiltonian operator acts on these bases. First we take the case of one-dimensional box. So for one-dimensional box, we know that this formula we have already seen in our previous lecture, that in one-dimensional box, the basis for the Hilbert space for the particle which is in the box is of this form, periodic, and psi pi n x by a, where a is the length or the size of a box. And for a state psi in terms of phi, now we want to do what? We want to expand this psi for one-dimensional box in these phi n. And if we expand it, this will be like this, that psi x of t from n is equal to 1 to infinity is expanded in terms of b phi n, and these b n's are actually over here you see are the coefficients. So it is like you can think of it like unit vectors. So these are the unit vectors, these phi's, and these are the weights or the coefficients which are telling us that how much projection psi has along, let's say, phi 1. So this will be determined from b1 and so on. But these coefficients are very important, and we will see now that we can define our probability of finding some observables value in terms of these coefficients. And this is very important point, that we can turn our probabilities in terms of Pn or these coefficients. So let's do that and find out that how the probabilities are, how these Bn's are actually probabilities. So in Dirac notation, let's first put this for sake of calculations into a bracket, Dirac bracket notation. So if I put this expansion of psi in terms of Dirac bracket notation, and then you can easily now see that this psi is expanded in terms of Bn and phi n. And then if we substitute this into the energy expectation value formula, this psi, if goes back to the, if you remember this energy expectation formula, this will be like this. So this is for the bra or psi star, and this is for the psi or ket. So you can see this is psi coming over here and psi star coming over here. Since Bn are some complex, we will see later on that it could become complex numbers, or then can be real as well. So over here you can see that we can put it this in terms of bracket notation. So energy is now coming in terms of these coefficients and the basis of some Hilbert space. So next, do some calculation and calculate the make this formula simple. So I will explain to you all the steps. So as I told you that this Bn is with the bra. So when we take it out, it will take star on it, and this Bl is with the ket, so it will not take it star on it. And then in the next step, we will act with the h on phi l, and when h act on a phi l according to Schrodinger equation, then it will have eigenvalue energy En, and when En is here, which is some real number, we can take it out and write it over here. And these coefficients n and l are taken different because it could be different as well, and summations are also taken out. Then in the next step, you know this phi n phi L with the help of Kronecker delta, which we did in the Hilbert space lecture, that this is equal to Kronecker delta. When n and L are equal, then it will be 1, and if not equal, this will be 0. But at least we can write it this orthogonality using orthogonality condition, that delta NL, and then we can drop it because it can be only 1 or 0, and this Bn n star and Bl could be equal to Bn mod square En. So after this simple calculations, we have now written E expectation value equal to Bn star En. And then we can see that since this is equal to the probability, because expectation value was equal to the probability, so we can compare these two formulas. So remember that this expectation value we have already written in terms of the probability formula. So now we have find out in terms of these expansion of phi n on Hilbert space, and these are the coefficients. So if you remember this this probability over here, that E is can be written in terms of the probability over here. So expectation value of E is equal to the probability, and then now we found again that the expectation value of E is equal to this thing. So we compare both of them now, and from here En is on the both sides, so it can be dropped, and we find out that the probability of finding En is actually equal to Bn mod square. And that was the important point which I was highlighting, trying to highlight, that the probability of finding the energy at any state is equal to the projection coefficients. So this Bn is actually a probability, you can say. Okay, so now we know how to calculate probability, because we can calculate these coefficients, and from these coefficients we can easily calculate the probability. Now the next step is to make it sure that we have done everything correct. We want to check the correct normalization, that whether this Bn are the correct values or not, whether there is correct normalization involved or not. For this purpose, we do this simple calculation, and it is actually very powerful condition that the psi star, that is the probability, must be equal to 1. So in simple words, we can say, if we say that electron in some space is present, so the probability of finding it at any point must be equal. If you do the sum of all the probabilities, it must be equal to 1 or 100%. So it is not possible that we say that electron is present in the box and then the probability is not equal to 1, because it could be that it is, for example, in here you can see that electron can be here, can be here, can be here, can be here, but the total probability excuse me, of the electron in this box is 1 or 100%. So from this requirement, when we put that psi star, that probability equal to 1, then we now do some simple calculations to check the probability normalization. So we put the value of psi star for bra, and then we put the value of psi, that is for cat, and then we do this Bn star and Bl outside. This is equal to Kronecker delta and Bn mod square, which is equal to 1. So we see that the coefficients, this requirement, and we call it an absolute probability in this case. When this is the case, when we demand that this is equal to 1, that these coefficients mod square is always equal to 1, then we call it an absolute probability, that is the particle is already there. But we can generally define this like Bn mod square, Cn mod square, and this one, and where Cn mod square is equal to phi n. So if this is a general case, even if these are not the bases which are already normalized, you will not get the value 1. So therefore this is the general case where the probabilities are normalized generally, and not with the orthogonal basis. Okay, so now it's time to give an example. So I will go towards the Hilbert space interpretation of superposition principle, and there will construct an example, illustrative example, from where then you will be able to understand this abstract presentation of superposition principle with the concrete values coming out. So in this example, consider that there is a particle that is in one dimension, that is a one-dimensional box, and then we have a state which is the superposition of phi 2 and phi 9. So let's say we have a particle which is in the state phi 2 and phi 9, or other states are 0, and these are the B's, B1, you can say B3 and B9. So, and normalized by 25 under the root. So we have value over here. For later on I will show you that this is B1 and this is this is the B3 and this is the B9. But let's say this is the state in which particle is there, and it is the superposition of two Hilbert space eigen values, eigen functions phi 2 and phi 9. These are the bases on the Hilbert space. Okay, so then we want to expand this our wave function, this psi over here, into the orthonormal eigenfunctions. These are called orthonormal eigenfunctions because they are not only orthogonal, that is perpendicular to each other, like phi 1 and phi 2, but with making an angle 90, but they are also normalized to 1. So that's why we call it orthonormal eigenfunctions. So this is the case we have already seen for the particle in one-dimensional box, that these are the orthonormal eigenfunctions. And then we can check first the normalization for the psi if we want to expand this psi into this phi n, for example phi 2 or phi 3. This is for the illustration just purpose. You can take phi 1 as well, phi 3, for phi whatever phi's basis you can check, but for just simplicity I have chosen these values and these eigenfunctions so that the calculations are simple. So let's check the orthonormality of it, or the normalization, that it is correct. So this is psi star will be 1 over 225, and this is 3 phi 2, 4 phi 9. I mean this is star, and this is a wave function, and it is complex conjugate, and since they are both, so 25 under root went to 25 because of the square, 25 under root coming from here, 25 under root coming from here. So we have just put the value of psi in here, and psi star in here, and psi here, and then you have to multiply each term with each, this with this, and this with this, and then again all the multiplication results in this one. And now you can see easily that phi 2 and phi 2 is equal to 1 because the orthonormality, phi 2 and phi 2 same, so they will result in 1, and this is equal to 0, and this is also equal to 0 because this is orthonormal, and this is again equal to 1. And if 9 plus 16 is 25, and 25 by 25 1, so you've seen that we have correctly normalized this wave function. That's why this psi is equal to 1. You see on the previous slides we checked that this psi this probability is must be equal to 1, and it is equal to 1, which means it is a correct normalization. If it were not the correct normalization, for example if we had 50 over here, so this would not be equal to 1. So that's why it would have came out wrong, not equal to 1, and wrong normalization. So in this case the normalization is correct. So after checking this normalization and seeing that everything is correct in this simplified problem, by inspection we can find out that B2 is equal to 3. This was a thing I was talking about, that B2 is equal to 3 over 25 under root, and the second coefficient B9 is 4 over 25 under root. And I will also explain that what it means for B2 and B9 and how they are connected with the probabilities. So with the probability, generally we say that if Bn is equal to 0 but n not equal, n2 and 9. So you can on the previous slide you see that we have B2 and B9. So all other B's are 0, all other coefficients are 0, that is Bn is equal to 0 but n2 not for the n2 is or n9. Or if you want to now calculate the probabilities, because probabilities are the B mod square. So what is B2? B2 is 3 over 25 under root, and if I calculate the square of it by the formula, the probability of finding the E2, the energy E2, is equal to 9 by 25, and similarly the probability of finding the energy E9 is equal to 16 by 25, and all the rest of the probabilities of finding the energy is equal to 0 for n is equal to. So what does this mean? It means that let's say if I have some replicas of the particles, that is 25 replicas. Imagine I have one-dimensional boxes, 25 of them. So first box there is a particle electron, for example. Second box and so on up to 25 boxes I have. Okay, 1, 2 and 25. So in 9 out of these 25 boxes, 9 I will have energy E2. I could have energy 2. Now we don't know exactly which 9, but if I make measurement on all these 25 boxes, so probability of finding E2 is 9 by 25, which means 9 out of 25 will give me E2 energy, will be in E2 energy. But what is the probability of E9? This is 16. That is 16 out of 25 will give me, because these are the only two possible energies in which particle could be, that is E2 and E9. And the probability of E2 is less, that is 9 by 25, because the B2 was less. And the probability of E9 is 16 by 25 because it was. So in this way you have seen that we were able to construct the probabilities. So in today's lecture, the superposition principle, we have seen that the concept of superposition principle is that we have a large number of replicas, and if we make measurements on each replica, then the value come out for any observable could be different. But what we can do then, we can take the average of them and calculate the probability for finding some value. Rather than finding an exact value, we can calculate the probability for finding some value. And this principle in general is called superposition principle. Thank you.